Hello again. I'm Shravan Srinivasan. I work on applied cryptography at Lagrange. Welcome back to my talk on Recproofs. It's a Merkle tree-based vector commitment scheme with updatable batch proofs. Today, I'm excited to talk to you folks more about the applications of Recproofs. So, before I kick start, let me give a brief recap of what I spoke last time. So I'm going to give a recap of the problem Recproofs is solving and how it solves. So we all know and love our Merkle trees. Merkle tree allows us to commit to an ordered sequence of value with a short commitment. Say when you have values A0 to A15, you can consecutively hash adjacent values, and you can do this recursively until you just have one value at the top, which is going to be the root of the Merkle tree. In addition to just computing the commitment to a vector of values, you can also prove an opening using Merkle trees. So say if I want to prove A5 is in this vector, I would give out these values highlighted in green, and any verifier can use these values to recompute the hash path from A5 to the root. And with that, they can recompute the root and check if this value is what they expect. If that is the case, they can accept this proof, else they can reject this proof. Um, Whenever there's a value changing in the vector, say in this example A12 changes, you can update the proof of A5 by computing the path where A12 to the root intersects with the proof of A5. In this particular example, it's going to intersect at the specific green node, and if I just update this green node, then we can update the proof of A5. Similarly, all proofs can be updated in this manner. So the focus of Recproofs is about batch proofs. Batch proof is a special type of membership proof. Rather than proving one element at a time, a single proof can open k arbitrary elements simultaneously. A new way of doing batch proofs is concatenating k individual membership proofs. That's why there's a key efficiency requirement that we need these proofs to be batch proof to be much smaller than the k individual proofs, and preferably we should be able to verify much faster. Uh, Current approaches are not updatable efficiently, at least. I'll tell you why this is the case. And the primary focus of Recproofs is how to build a batch proof that is also updatable. So a quick run through of a name example. Let's say that an inefficient way of doing batch proofs is to concatenate all the proofs. So say if I want to prove that A2, A4, A5, and A15 is in this batch, I would give out the individual membership proofs of A2, A4, A5, A15, and all of them put together would make up the batch proof of this set. Unfortunately, this has a large proof size. It's going to be k times log n asymptotically. And one of the good things is you can, just like the way you update individual proofs, you can easily update this batch proofs just by invoking the same individual proof update k times. You can get rid of some of the problems like being a large proof size by compressing the batch proofs using snarks. However, it has its own drawbacks. Whenever an element in the vector changes, you have to recompute the entire batch proof from scratch. And whenever the size of the batch changes, you have to figure out how to reconfigure your circuits such that you can batch more elements in the vector. So the rec proofs primarily uses recursive snarks, and it can update batch proofs in log n time. And we can extend rec proofs to verify MapReduce style computation, even when the underlying data changes. For example, when you want to verify that certain elements of the Merkle tree are greater than some value, you can generate a nice proof which in fact attests to this any predicate of your choice. So I'll be talking more about the applications today, specifically on the BLS key aggregation and the digest translation later during the talk. So a quick rundown of how rec proofs work. Let's say that you have a Merkle tree which is going to contain these values A0 to A15, and the green values are the hash values. Now say that you want to compute a batch proof for A2, A4, A5, and A15. You would have a pruned partial tree with just these green values. And in addition to having these Merkle hash values and so on, you would need something called as a canonical digest. What this does is essentially at each node in this prune tree is going to have something called as a canonical digest, and that is defined with respect to the batch it's trying to prove. So essentially, if you look at the root node C here, it's going to contain a set in blue which consists of A4, A5, and A15. So these are all the values that are in this under this node, and a node rooted at this location in the tree. If you look at A12, C, CL, A2, A4, and A5 are the only values of the subset that are in this subtree. If you look at CR, A15 is the only value that is in this subtree, which belongs to the subset, the original subset. So I've highlighted the subset in blue, which we call as node subset. When you compute a short accumulator digest of this node subset, we call that as a canonical digest. So in addition to computing these values in blue, we also require a snark proof at each internal node of the pruned Merkle tree. So essentially what the snark proof says is all the set values, which are highlighted in blue, and the Merkle values, which are in green, are consistent and the entire subtree is valid. So you keep on building such recursive proofs, which will attest to the values which are under the subtree. And the one which you have in the top is essentially going to attest to the fact that the subset A2, A4, A5, and A15 is in this vector. And the Merkle tree digest of this entire vector is going to be C. So, and the root pi, the proof pi, which is at the root of this tree, is going to be the single batch proof that's going to prove that these elements are in the batch. So whenever you want to update an element in this batch, all you have to do is just recompute the values along the path from the leaf to the root. And this way you can compute a new updated batch proof. In this example, it's going to be pi prime. So we can generalize this approach to perform MapReduce style computation. Say that you have A0 to A7, 8 values in this vector. First, you assume that you have committed to this vector using Merkle trees and Z's commitment. Then you can perform MapReduce style operations on this specific tree. So when you perform map, you'll get a specific output, and the reduce operation is going to take the values from the previous to previous level and combine them, and it's going to give out another value. So in addition to doing the membership parts, you also attach a proof pi LL, which attests to the fact that the reduce operation was done correctly, and the Merkle digest at that specific subtree is also correct. You can do this recursively all the way to the top, where you can take the results from the previous reduce operations, combine them together, and reduce it one more time, and attach a proof that the reduce operation was performed correctly. At the same time, the hash values, the Merkle hash values in that subtree are correct. And the proofs that were in the previous level were also correct. You can do this all the way to the top such that the root has a proof pi, which will attest to the fact that the MapReduce operations in this tree were performed correctly. At the same time, C is the digest of this vector. So let me jump into more about how we use Recproofs in the context of blockchains. So blockchains have incremental state updates, meaning that between consecutive blocks just updates the state of the blockchain by whatever transactions that are contained in the specific block. So, and Recproofs are designed to be such a way that it can incorporate such incremental updates. You can also think about how to parallelize it in Recproofs and such a way that you can apply multiple updates simultaneously. So jumping a little bit more into the details of how the state looks like. So essentially in a typical blockchain, the state is going to be the account balances and the contract, smart contract storage. And when you want to make statements about, say, specific contract of your choice from some memory slot, first thing that you would do is to prove the membership of that specific memory slot. However, making statements about just one memory slot is not that expressive. And you would have to batch proofs when you want to make statements about multiple memory slots simultaneously. A key thing to note here is whenever a new block comes in, this batch proof might change. And if you use standard naive approaches like the one I mentioned using snags, you might have to recompute the proofs from scratch. However, on the other hand, when you use Recproofs, you can update them in logarithmic time, and you can keep the batch proofs up to date based on the updates that happen. So let me concretely tell you how this works. Let's say that there's a specific memory slot in the contract which keeps track of some specific price or some exchange value or something, and you want to compute a moving average to see how it goes about. So a moving average is going to be in this particular example, the moving average window is going to be of size k, and you want to take the last k values, compute the average over it, and return this as the value at instance k. So one way to do this is first you take the values p0 to p7, you build a Merkle tree out of it, and then you perform the Recproof style map reduce at each level. So in this specific instance, the reduce operation in purple is going to be p0 plus p1, and so on with other values. And the snag proof here is going to attest to the fact that everything that was done in the subtree was done correctly. And you can propagate this through multiple levels where you can have take the results from the previous reduce operation and reduce them again, and attach a proof that the subtree was done correctly until you get to the root. At the root, you can simply divide them by the size of the tree, and you get the average. So in this case, the proof pi is going to attest to the fact that this is the specific moving average at this specific instant. So let's say that when A0 gets replaced by A8, you can just change that specific value in the vector and recompute everything along the path from P8 to the root, and only those values have to be updated while reusing other values and other proofs and other results of the Merkle tree and the Recproof tree that wasn't touched. So that's the general flavor of things. So once you have a moving average style approach, you can try to generalize this to compute standard deviation, which is a useful metric in other scenarios where you want to compute the volatility of some specific option and so on. So you can use such techniques to do it. So a new way of doing it is just to follow what we did in the map in the moving average example. You compute the total sum, and then you can use them. You can use the mean to compute the standard deviation. Of course, there are clever ways you can go about and computing this and so on. So in general, you can generalize this to multiple any making to, to prove queries over any storage slot. Say that there's a gamified contract that wants to query some other contract based on some predicate. For example, you want to select star from some specific contract where the owner is XYZ. What you would do is you would just filter out the values based on this specific predicate. In this example, is going to be owner, and then build a Recproof style batch proof that's going to not just attest to the subset of values that are in this tree, it's also going to attest to the fact that you filtered correctly and so on. So jumping into the examples of other examples, how where you can use Recproofs in a little bit more detail. Say that you want to aggregate BLS public keys. So say that a smart contract has n validators and the public keys are stored in each slot. Now the goal is to compute the public key, aggregated public key of a subset of validators. And you also want to compute the size of the set. At the same time, the set can change across blocks. So this is useful in emerging applications and new blockchain systems where the number of people who signed at this instance might not show up in the next one. At the same time, you want to compute an updated batch proof. At the same time, an updated aggregated public key that can be used to verify if certain threshold of people have signed a particular message or a block. So in a little bit more detail, so we want to compute the aggregated public key APK, and we want to make a claim that T out of n public keys have signed this, and the Merkle digest of such public keys is actually C. So it follows the same recipe which I've been showing you. So you have these public keys at the bottom. You first compute the Merkle root digest. You perform, let's say that in this example, K2, K4, and SK5 have signed it. Then you just perform the first operation in this example is going to be map, where there's just one have signed so far at the specific level. So it's going to be 1 comma the public key. And when you go to the next level, you can perform a reduce operation which takes in the results from the previous level. So in this, let's say if you look at the subtree of 4 and 5, you can see that the count is going to be 2, which says that 2 nodes, 2 public keys have signed under this subtree. And the product of those two public keys is the aggregated public key for these two public keys. You can keep doing this until the top while attaching a snark proof, which will attest to the fact that you have done this computation correctly at each level. At the previous level, at the next level, you'll also check if this snark proof is correct. At the same time, if these results were done correctly. At the end, when you have at the top, the count is going to be 3 public keys have signed, and the product of them is going to be the aggregated public key, and pi is going to be the proof that attests to the fact that the map and the reduce operation industry were done correctly, and the values you have received is in fact correct. So in fact, another example of using this style of primitive is doing something called as a digest translation. Say that you have n values in the vector, and you compute the Merkle digest using a hash function h1, which is used in let's say in the base chain or something where with strong security properties such as SHA-2 and so on, and it also has been optimized at the machine level. However, at the when you want to do something like a rollup, you would preferably want to have hash functions that are snark friendly. So let's say that you have another Merkle digest C2, which is computed using the hash function h2. In this example, it's going to be, say, like something like Poseidon, which is snark friendly over the same set of data. We can prove that these two digests were computed using the same n values. So this particular example of digest translation is useful in rollups, as if you want to compute an inclusion proof at the rollup level using SHA-256 proofs, it's going to be more expensive to verify. So to a little bit more in detail, so Merkle digest C1 and C2 computed using hash functions h1 and h2 respectively correspond to the same n values. We want to prove the statement, and it is useful in rollup style applications. So the recipe is pretty much the same as you would have guessed. So you would essentially compute the Merkle digest using C1, which is already there in the base level base level, and then you would perform the map operation. In this case, it's going to be the identity operator, and you perform reduce operation, which is going to be using the hash function h2, which is going to be snark friendly. In the end, you're going to have another Merkle digest C2. It's essentially it's computed using the hash function h2, and the proof pi, which states that C1 and C2 were computed over the same set of data A0 to A7. So yeah, in essence, you can use Recproofs to perform many MapReduce style computation. One key aspect which I did not touch today was how do you provably extract, transform, and verify, and so on. So that's for some other time. But once you have the data transformed in some particular fashion, you can run Recproofs style proofs to compute that the computation was done correctly and the values are indeed correct. At the same time, you can generalize this approach to in multiple directions. Like say if you want to change the arity of the tree so that that is in line with the actual, let's say something like Ethereum or so on, you can consider doing that. You can, for example, in the example which I gave you about the digest translation, the trees might not have to be of the same structure. You can think about further extensions to Recproofs. And yeah, stay tuned for our subsequent releases about this work.
Amazing. Siobhan, that was once again super educational. If you don't mind keeping the slides on the screen, because I do have a question
Of course.
On one of the slides. I've actually had a comment about entropy in my Twitter bio here for a little while. So I'm curious if we could go. It was relatively early, maybe like middle early in the slides. And I remember the slide. It said that this proof format, here we go. So helps to keep low entropy in storage state between blocks. What does entropy mean in the context of blocks on the blockchain?
So I was referring to the standard example of entropy as a measure of randomness, meaning let's say that you have a state at the end of some block, and the only transitions that are going to happen on top of the state is going to be the transactions that are included in this. So, and the number of things that can go inside is going to be limited by the amount of transactions you pack. So it's going to be some few small updates that are going to make changes to to the state, and at the end of this you're going to be transformed as a new state, and yeah, that's going to be the most up-to-date state. So you don't have to be worried about many things changing simultaneously. We will have to be worried about a reasonably few things. I'm not quantifying anything, but it's reasonably few things are changing. And essentially, if you just replay all of these transactions, you come from Genesis, you would end up with where you are. Yeah.
Okay. That, I guess, a quick follow-up, is that because the Merkle tree extends the leaves of the tree only in the direction where there's an update to the state? Let's say that the transactions, on the left side of the tree don't have any updates to them, then they won't have any more leaves. There's no more complexity on that part of the proof.
Yeah, one way to think about it is like, let's say that you have all the slots, and not all slots might change simultaneously. Only few slots might change. Just forget about right and left. It's more about picking a few slots, and only few slots might change based on value. And when you have such changes, you can, when such changes are happening to the blockchain data or the state, you can map such updates even on the Recproofs style. So you can make such changes is what I was trying to convey here.
Cool. Okay. I think I understand.
Gotcha. Yeah, I've got one as well. I think maybe closer to slide 15 or 16. If you could go over there as well. One more. Yeah. So this equation here has a lot of pieces, and to understand any of these equations, there's obviously a deep level of math and cryptography experience required. But I'm curious from a personal and from an academia perspective, how you're able to kind of take equations like this, which you can formulate on paper, and through programs and proofs, and then kind of translate that theoretical and kind of proof-based math onto like a code language. And I'm perhaps not asking that correctly, but I guess what I'm curious about is taking this math and implementing it into the code that is required for a ZK proof.
Yeah, so I have the privilege of working on both sides of the aisle. So first, when you come up with some scheme, you're going to formally write down with, let's say, with a certain set of mathematical properties. Let's take KCG commitments for an example, a specific property about polynomials that are being satisfied every time when you give out an evaluation proof. So now once you have something like that, you would try to prove why it's correct. So you would go through the start exercise, like in standard cryptographic class, you would go through the start exercise of saying that, hey, if the adversary can break, what are the possible other, if someone can break the system, can I just translate this attack into breaking something else? So what we would typically do is like we do write some sort of saying that, hey, if someone can break this, they can also break some other cryptographic assumption. And once and we know that assumption is not broken, and we retrace back saying that you can't do it. So and once you formally have proved and done these formally proved the protocol, then comes the fun part of bringing it to life in the real world. So at that point, it's more about finding optimizations, finding out if there are any gaps in the way the protocol is written, or in the way some case which was not covered, or and so on. So that comes up during when you actually implement. You would see, hey, this is the performance of the system, and this is what we expect. So, and this is a very bad way. This slide is a very bad way of giving specs. When I want to write some protocol, I wouldn't want to be as abstract at this level. I would want much more at a concrete level. There are many ways to, in fact, to implement a standard deviation. And standard deviation is fine, but when you want to do something like a snark system, there are so many ways to do all of the protocols that are listed, and with each being really fast versus really slow. So you want to make sure that you use the appropriate tools and so on. So it's a beautiful process, right, from writing the protocol down to bringing it to life in writing code. And yeah, it's more about playing the role at each part, like writing the best code when you do it, making sure that when you write the protocol, you're thinking through that everything was done correctly and formally. So you have to wear multiple hats. I'm sorry if I'm not sure if that answered the question.
No, it's clear that it's a multi-step process requiring different kind of ways of thinking, which is why it was super interesting to me, because to me it seemed like the way of thinking of deploying contracts on a blockchain is definitely different than the way of thinking of answering a proof or a kind of math equation. And yeah, I wanted to touch more kind of on some of the earlier slides as well, if you don't mind.
Sure,
One more question. I think around like slide 5 or 6, maybe. We talked about the membership proofs, efficient batch proofs. Go to, yeah, this is an interesting one. Okay, yeah. So Recproofs. This was the one. So basically, I'd like you to explain why using recursive snarks. And I think that you did a pretty good job in the slide here. But the recursive snark aspect is interesting because it's something that that we've heard about, with something going back to all the way like Zcash, right? All the way back to that kind of technology. And then now I know Starknet is pioneering this kind of recursive snarks, and they even have Starks. But why is using recursive snarks the go-to way to basically establish these batch proofs? So just why is that technology for these proofs so prominent? And I guess is there other technologies that are as good or as battle tested as well?
So you are essentially, we end up using recursive snarks when you want to prove about a previous snark that was computed. So that when you encounter such scenarios, your best bet is using something like recursive snarks and go about it. So and in the context of Recproofs, essentially what we do is, let's say that if I want to compute pi LL, I want to prove that the previous subtree was done correctly. So rather than tracing it all the way back to the leaf, I would simply have another proof that says that pi LLR is correct. So if pi LLR is correct, then I know that whatever is inside that is correct. So and pi LL has to just make sure that whatever is happening in that specific level is in fact correct or not. So these are the examples.
So the snark is able to to basically prove that data happened in that last block, or in that last, for lack of a better term, section, and then kind of transport that back in or forward into the next section to kind of keep the data in the chain valid.
Yeah, exactly. That's a very nice way to think about it. Just making sure the previous checkpoint is correct and so on. So recursive snarks have been very ubiquitous, and people have been using it for a variety of stuff. However, there is we are moving at a stage where the performance is have tremendously improved since 2008, when people started thinking about proof composition and so on. And we are at that exciting times where there are plenty of ways to do recursive snarks. One is like you can write it inside a circuit. There are new schemes like folding schemes and so on. So there are new ways to think about how to prove something about the past. That's I'm very fortunate that the state of the art has been coming forward with a lot of great minds. I'm happy to be using them for my work.
Yeah, that's awesome. Yeah, thanks for that answer. That makes it super simple, and that's kind of what it's about for us here with this entire series and with this video and speaking with you. Is, some of these concepts obviously are quite high level and they require years of academic studies, but being able to kind of put them into the terms of something like a checkpoint or something like understanding how blocks are kind of processed and created on a blockchain. It kind of illuminates that, while this is definitely out of reach for perhaps from a coding or math perspective, from a high level understanding perspective, it's certainly not somewhat unattainable. So thanks for that. I think one more question, if you want to flip through the next slide, or perhaps Rob has one, but I think I've got one more if you have a bit more time.
Sure.
Yeah, through this next one too. Okay, sorry, through this one. Okay, so yeah, back to kind of this state here, and I know Rob asked about the entropy, but I'm kind of more curious about the diagram that's happening here, and basically what we're seeing is kind of explained in these bullets. But when you say genesis, is that like the beginning of the block or of the chain?
Yeah, so Genesis block is where it all started, right? Bitcoin has this Genesis block and so on. So essentially, all of us agree that this is going to be the first block of this blockchain. And from there, you keep mining new blocks on top of it, such that all the way, when you trace back, it all the way points to the first Genesis block, which we agreed on. So, the figure which I was trying to go for here, which essentially says that, hey, the state is essentially going to be, you can think of it just like a fancy way of thinking about it. I mean, a simple way of thinking about it is just a table. You have some indices and you have some values. And when it's a human, it's going to be, each index is going to contain an account balance. If it's a smart contract, you're going to contain some information about the state of the contract. So this is the only absolute state that is relevant right now. And when you want to make statements, about anything about this, the state, and how does Batch proofs help, and that's where I was getting at. The figure is more about putting them all together. You can't put the entire table in the block, so you want to have a small digest, some nice way of representing them, and that's where Merkle trees, Merkle Patricia trees, and such cool data structures help us do it.
I'd like to point out
I think Rob's got something.
Yeah, one thing about this diagram that I'm just noticing now is that the arrows between the Genesis block and block B are actually pointing backwards in time. So this diagram is to show the proof mechanism of proving the validity of block B, because you can trace these proofs all the way back to the Genesis block.
Yeah, exactly. So when I mine the block B, I would make sure that I would take the information from block B -1. I would put them in the current block, and then I would actually mine block B. If you're more familiar with proof of work kind of idea, so you have to take the hash of the block B -1, put it in the next one, and only then you try to mine, and so on. This is a common case with every blockchain, where we pretty much want to attest to the fact that I'm building on top of B -1.
Yeah. And then the concept here in the middle about the state tree containing account balances and contract storage. This is something that I've heard in various podcasts, and I'm sure people who are listening have heard of the blockchain state. And you kind of described it as indices and kind of tables of data. So what's the best way to think about the blockchain state in like an abstract way that's like understandable? I know it's tough to kind of just throw that at you, but like, what is like in the realm of the chain of blocks and of the transactions in these blocks, the state of the blockchain is thus represented by the account balances of the actors, or of the wallets, or of kind of the ledger and the contract storage. Could you kind of illuminate on the state? Kind of
Sure. So let's, for the sake of simplicity, let's forget smart contracts are not there. So, and it's just like a classical system where I want to transfer money from one user to another. So I would have, let's say, let's consider like going to a centralized bank or something, it's one way to think about when you want to do something like in a centralized bank. There's a huge fancy Excel sheet which says that there is going to be a column on the left. It's going to have some information, my ID, saying that this could be my ID, and this is the balance I have. The next row, it could be the ID of yours. Then it could have some specific balance. So you can have this entire huge table. So when I want to transfer money, all I have to do is say that, hey, I want to transfer a few dollars from my account to your account. So at the end of the day, the transactions change this table by moving value from one to another. And you want to make sure that I can't transfer more than what I have and so on. And that's where the validity of these things come into play. So it's a glorified way of seeing this. This is a huge table. One side contains the IDs, the other side contains the account balances. And you can start generalizing this using contracts and so on. You have some address about the contract, and you have the digest about the contract state, and you can do this. So that's the fundamental building block of accounts-based blockchains. And and when I mean the state, I essentially glorified way of referring to this huge table. That's what I do.
Yeah, and then this huge table basically takes up storage. Like it is data which requires storage. And so when I'm gonna extrapolate this all the way back to like a ZK rollup or a rollup, when a transaction when a block is then produced and in this sense by a sequencer or by some entity, and then is being redistributed back to L1 to basically go to Ethereum. The state of the block in the ZK proof, that data is that the reason why you are paying to then process back to Ethereum? Like you're paying to take this data in the state of this ZK proof or of this kind of block on, let's say, in L2, and you're paying to put that data back onto the main chain. That data is the reason that you're paying, or it's the Ethereum block space, but the data that you're transferring is what's in that proof. And I kind of answered that there myself, that you're paying for the Ethereum block space, but the data in the state is what is being transferred to L1 in a sense, or am I kind of missing something there?
Yeah, you are correct. Essentially, you can think of it like the smart contract has its own ledger that's part of the big ledger which I was talking about. So when we make transactions within the rollup, we just modify the small ledger at the contract level, and that essentially when you make a bunch of changes, like you, me, Rob, and so on. So when we make such changes, that table gets updated, and we want to reflect this back to the master table, which is going to be the one at the L1. So we have to reflect this somehow, and just like the way you said, we have to incentivize miners to do this, and that's why we end up paying some fee to the person who does this for us.
Yeah, thanks. Makes sense. So so the blockchain state. The state is an interesting way to state is an interesting word to describe what is encompassed by the states. Perhaps I'm not even sure what you could even say, like a storage ledger or something.
One of the ways like we've talked about it before is like the constellation of all the account balances in this table. Like the configuration of accounts and balances at any given time or any given point, is considered the state. It's like the status of each account. Is that sure, Ron? Is that fair to say? It's
yeah, sure. You can. The current state is essentially what values do you have in that. So coming back to your question, Andy. So people used to classically call this a state machine replication, and with Bitcoin and so on, we started calling this as blockchains.
That's how that came.
Yeah. So the abstraction which the classical literature was trying to give is, you could have 10 machines running some piece of. You could have 10 machines, but all of them should give an illusion that they are just one single monolithic machine. So when I interact with it, I shouldn't know that there are 10 machines that are going underneath, and any of these 10 machines could fail and so on. But for a user at the external level, it should pretend as if it's just one machine. So, and how do you do it? You just make sure that every machine keeps replicating the steps of computation that needs to be done, and so on. And that's how people called it back a while before Bitcoin, and now it's going to be now it's called as blockchain.
Yeah, nice. Bitcoin, not blockchain. Yes, someone. My last question here is basically can I imagine this block be, let's say this is ZK sync error, right? Or ZK-rollup, which can fit here, right? And so am I right to say that application 1 it being Uniswap, application 2 being Aave, 3 being 3 dots, nobody likes that one anyways, and 4 being some other. So each of these apps contribute the state in that time period of that block, a unique ledger, if you will, which is then basically bottled up or brought together through the Merkle tree and then all put into one state. So the two ledgers of the first application state come together, then application 1 and 2 come together, then 2, 3, and 4, and all into one. Is that what is like happening when these blocks are being created and the states are being pulled from these different applications, or is that all?
So I'm simply what you said is pretty much the case in generic scenario, but the specifics slightly differ. Like I assumed it to be a binary tree and so on. So that is not the case. Ethereum, for example, has its own data structure. It has a different kind of tree called empty trees, and it uses such ways to organize the updated state and so on. Yeah, that's a nice way of thinking about it. These are slight specifics which we can figure out once we are actually coding it, but at the abstract level, we can simply think of them as a binary tree, and we can keep doing it. Values could change. Some values might not change. Some contract might not have changed at all in this particular block. So it will still have the same previous state, what it had. So for example, one of the Uniswap contract could have changed, its state could have changed, then you would have just updated that specific address. So yeah, that's what I was going for this figure.
Yeah, thanks.
So it's clear that you understand blockchains at a very, very deep level, and you've done
so.
I mean, I think so. And you've done the research to understand like the components and the elements of like both the proof mechanisms and then the architecture overall. My question is, what is the goal of your research?
So now at Lagrange, we are very motivated to have the best system out there to do data parallel computation. So when you want to run arbitrary queries on blockchain, say some information about the past, whether it's historical or whether it's current one, what is the best way I can give you a proof that says that this query was performed correctly, and you can use this without pretty much a lot of overhead. So just best way to think about it is how do we do a verifiable map reduce on the blockchain data is one way to think about it. But it's more about generalizing it to arbitrary queries, and how do we go about doing it the best way is what I spend most of my time these days thinking about.
Very cool. Yeah. So a general purpose machine for recognizing and proving data across state replication machines overall.
Yeah, there are so many layers to it, but in pretty much, essentially, we want to run queries on top of blockchain data, and how do I prove it to you in a verifiable way? And it has applications which, for example, is the ones I listed here. And I'm hoping that our viewers are going to suggest a few more and what they think it's useful for them.
Yeah, I mean, what immediately comes to mind is a form of data availability similar to Celestia. I mean, I'm sure you've thought about something like this, but if you have like inputs of data, then you could also you could prove that data to these blockchains. Because if you're proving, like if you're making queries and you're proving those queries from the blockchain, it makes sense that you can almost like make that backwards compatible so that you could then like supply the blockchains with data as a data availability solution as well.
Yeah, so there are numerous challenges in thinking through all of these parts. But yeah, one way to think about it is like, yeah, you have this data and can I just make queries on it and answer some specific thing that is of interest to me? Yeah, that's a nice way to think about it.
Awesome. Well, I'm all out of questions. Thank you so much
for going for hours, but I really appreciate your time, Shravan. It's been a pleasure. They don't teach you this in college. Well, maybe they do, but they don't teach you this in any other place other than the Rollup. So, thanks for coming on, Shravan. It's been an absolute pleasure, and it was enlightening and very educational. So, thank you.
Yeah, it has been a pleasure to talking to you guys. Yeah, I enjoyed both of my talks with you guys. Thank you.
Likewise. Cheers.